Hello everybody, this is notes number 37 today, and today we're going to learn about the mysterious word logarithm. So we're going to define logarithms today, and we're going to start with what we know about exponential functions, and then we're going to figure out the inverse of exponential functions. So let's take this simple one, the exponential function y equals 2 to the x power. The domain of that function would be all real numbers, because you can take 2 and raise it to any real number power. And the output that you get is always going to be a positive number. So the range is y is greater than 0. All right, so what about the inverse? Well, the equation of the inverse we're going to come back to in a moment. But one thing we know is that for inverses, the domain and the range switch. So the domain would be x is greater than or equal to 0, or excuse me, just x is greater than 0. And the range would be all real numbers. Okay, well, let's find some ordered pairs. So for this exponential function, if we had x equals -1, 2 to the negative first power is 1/2. If we have x equals 0, 2 to the 0 power is 1. And if we have x equals 1, 2 to the first power is 2. So for this inverse, whatever it happens to be, we know that for inverses, x and y coordinates switch, so we could list some ordered pairs, 1/2 -1, 1, 0, and 2, 1. So remember how for the basic exponential function, the y-intercept is always the point 0, 1? Well then, for the inverse of it, the x-intercept is always the point 1, 0 for the basic function. Let's see, what else can we do? How about the graph? So remember what the graph of y equals 2 to the x looks like, exponential growth. We'll just make a rough sketch. It looks something like this, passing through the point 0, 1, having an asymptote of y equals 0. So then our inverse is going to have an asymptote of x equals 0, a vertical asymptote. It's going to pass through the point 1, 0. And it has to be the reflection of the other graph across the line y equals x, so it's going to look something like this. Now, if you were graphing them on the same set of axes, and you drew in your reflection line, you could see that reflection a little bit more clearly. Okay, for today's lesson, we're not going to focus on the graph so much. We're going to focus more algebraically on the inverse of an exponential function, and then next time we'll come back and do more graphing. So algebraically, let's find the inverse of y equals b to the x. Well, we know for finding inverses, the first thing we do is switch x and y. So that would give us x equals b to the y power. And then the next thing we do is isolate y. And this is where we get stuck. Now, usually when we're doing this lesson in class, I ask students to make suggestions about what you would do to isolate y. And typically I get this for a suggestion. People say, well, maybe you could take the y-th root of both sides, like this. The y-th root of x, the y-th root of b to the y. I understand the reasoning behind that suggestion. It makes sense because it does isolate something. It isolates b. Well, that wasn't the goal. The goal was to isolate y, not b, so that didn't work. So typically we think about it a little bit longer. We try to figure out what mathematical operation that we already know could we use in order to isolate y, and we come to the conclusion that there isn't one. There isn't one we already know. So what do mathematicians do when they come across a dead end like this? Do they give up and say it's not possible? Well, let's think back to what we've seen in the past. Remember when we were doing something like this, the square root of -1? And we discovered that mathematicians don't say it's impossible, they just define something new. And that's where we ended up with imaginary numbers. If you go back even farther than that, think about mathematicians who used numbers like 1, 2, and 3. And they decided they wanted to figure out how to go the opposite direction, and then they defined -1, -2, -3, the negative numbers. So mathematicians have a history of defining something new. So this is where logarithms come in. It's defining something new. The purpose of a logarithm is just to have a new operation that will allow us to isolate y in this equation and allow us to have something that's the inverse of the exponent. So if you break down the word logarithm, the roots of the word logos basically means word. One of its meanings is word. And a rhythm, think about arithmetic. That basically means numbers, count, etc. So what we have here is a number word. The word logarithm, it sounds scary, it sounds different. Maybe you have never used it before. It's just a word that means number word. Okay, so let's not be intimidated by it. So here's how we write this. We write y equals log base b of x. Now, log is just standing in as a symbol, similar to the symbol square root or the symbol sine if you were doing trigonometry. It's standing in as a symbol. We still have basically the same relationship we had up here. It's written in a different way. These are the exact same statement. And so they mean take the base b, raise it to the power y, and you get the result x. Now the result I usually call the argument. So what have we done? In the exponential situation, we would input the exponent. We would output the result, let's say, what you get after you raise the base to the exponent. Well, in the inverse, our output is actually the exponent. So here the input was the exponent. In the inverse, the output is the exponent. And the input is what you would get after you raise your base. Oops, that's not how you spell input, is it? Talking and writing at the same time. The input is what you would get after you raise your base to the exponent. Okay, so what we need to do is practice this a little bit. I think first I probably have the definition written here. Well, kind of. Okay, so this is the key to remembering logarithms. Y equals log base b of x is equivalent to x equals b to the y. It's just the way to write it with y isolated. So let's go through some examples and we'll write one form when given the other form. So you can see in this first example we're given the exponential form. 2 to the third power equals 8. We know that to be true. Let's write it in its logarithmic form. So we have log base 2 because the base is the same for either form. The 2 is a subscript. So we have log base 2 of 8 equals 3. Remember, the output is the exponent in a logarithm. So it still means take 2, raise it to the third power, and you get 8. Let's do another one. Another one that we should recognize as true, 10 to the first power equals 10. So the way we write that in logarithmic form is log base 10 of 10 equals 1. Now let's look at an example where we actually have the logarithmic form and we're going to write the equivalent exponential form. So you ask yourself, what's the base? It looks like the base is e. By the way, when we say this statement right here, here's how we say it. Log base e of 1. Notice the words I put in there. I put the word base and I put the word of. So I'm going to say it again and I want you to say it with me. I'm going to say it 2 times. Log base e of 1. Log base e of 1. Say this one with me. Log base 10 of 10. Say this one with me. Log base 2 of 8. Okay, let's go back to the third one and let's write it in its exponential form. Our base is e. We're raising it to the 0, and the answer to that is 1. Let's do a couple more. Log base 3 of 81. And I accidentally made a mistake on that one, didn't I? That should be a 4. Okay, log base 3 of 81 is 4. The base is 3. We raise it to the 4th power, and that gives us 81. Those two statements are equivalent, just written in a different way. One more. We have log base 1/2 of 128 equals 7. Well, maybe we can't do this one quite as quickly in our heads. Let's see. If you take 1/2, well, I guess we can write it. We just have to think about if it's true. If you take 1/2, the base, and you raise it to the 7th, do you get 1/128? Actually, that seems right. I know that if you take 2 to the 5th power, you get 32, so 2 to the 6th power is 64, so 2 to the 7th power is 128. Okay, here's some things you won't see. Hopefully you won't see them. Log base b of 0. This would mean that you're taking a base b and you're raising it to some power, and your answer is 0. Well, we know that that's not possible, assuming that our base is a number that's greater than 0 and not equal to 1, as we defined our exponential bases to be. So because that's not possible, we shouldn't see an expression like that. You also shouldn't see log base b of a negative number, because that would mean that you're taking your base, a positive number that's not 1, raising it to some power, and you're getting a negative number. Well, that's not possible. We know that the range of exponential functions is y is greater than 0. So you should always get a positive in this place. Okay, so here's our definition of a logarithmic function. Y equals log base b of x if and only if x equals b to the y, where the base is not 1, the base is positive, and therefore x is also positive. Okay, we're going to look at some of our basic properties today and do a little bit of practice. Log base a of a. Here's an example. Log base 7 of 7. So you say to yourself, 7 to what power gives me 7? It would have to be 1. 7 to the first power is 7. So no matter what your base is, assuming that it's positive and not 1, log base a of a is always 1. Log base a of 1. Here's an example. Log base 2 of 1. Okay, so you say to yourself, 2 to what power is 1? It would have to be 2 to the 0 power is 1. So no matter what your base is, as long as it's not 1 and it's positive, log base a of 1 is going to be 0. So you can have 0 in this position, because 0 can be your exponent. You also can have a negative in that position, because you can have a negative exponent. You just can't have 0 in that position or negative in that position. Okay, log base 10 of x. Log base 10 is called the common log. It's used very often. And so it has a special symbol. We just write log. Log base 10 of x is written as log of x. Log base e of x. E is a special number. We talked about it last time. It has to do with the growth of money, but also the growth of other things in nature. It's known as the natural log. So if you see ln, you actually just say natural log. If you see natural log of x, it looks like ln x. And that is the same as log base e. All right. Now, remember from when we learned about inverses that if f of x and g of x are inverses, their composition will be x, because inverse functions cancel each other, like plus 2 and minus 2 times 3 divided by 3. So f of g of x will be x, and g of f of x will be x. So imagine that f of x is b to the x power, that's an exponential function, and g of x is log base b of x. That's a logarithmic function. They have the same base. They are inverses. So that means that b to the log base b of x will just be x. Inverse functions cancel. This is an example of having f of g of x. See, we put the g of x function inside the f function. That was g. That was f. An example where you might see this played out is expressions like this. Suppose we have 3 raised to the log base 3 of 9? Well, when you see the base 3 and the log base 3, you realize you have inverse functions, one inside the other. They're going to cancel each other, leaving you with just 9. And if we put them the other way around, this would be an example of g of f of x, because the f of x function is inside the g of x function. That's also going to be just x. So you might see this if you saw something like, oh, I suppose log base 11 of 11 to the 5th power. Then that would just be 5. You could also see something like log base 5 of 25. Well, you don't see the 5 and the 5, but you could change the form a little bit and you could write it as log base 5 of 5 squared. And then you would see your logarithmic function canceling with your exponential function, leaving you with just a 2. Okay, we're going to wrap up this lesson doing a few examples. Evaluate without a calculator and evaluate with a calculator. Suppose you have log of 1/10. Remember that when you see log, it means log base 10. So you say to yourself, 10 to what power is 1/10? And the answer is -1. So you really don't have to do anything besides just think it through. There's really no work to show. Number 3, log base 4 of 64. So you say to yourself, 4 to what power is 64? 4 to the 3rd power is 64. So the answer is 3. Natural log of e squared. Okay, so you remember that natural log means log base e. So this is equivalent to saying log base e of e squared. Now, do you see the exponential function canceling with the logarithmic function, leaving you with just 2? Or in other words, you could say e to what power gives me e squared? Well, it would have to be e to the 2nd power gives me e squared. So our answers are 2 and 3 and -1. Now with the calculator, and you just follow whatever rounding instructions you're given in the problem. In this case, round to the nearest thousandth. So that would be 3 decimal places. Log of 50. So grab your calculator, look over here next to the 7, there's a button that says log. That is log base 10, that's common log. So you just have to press it, type the 50, and there you go. And we can round that to 1.699. Natural log of -12. Okay, so right below the log button, you have the ln, the natural log button. So you can press natural log, type in -12, press enter. Okay, I got an error. Why did I get an error? Why did it not like that? Well, remember the domain of a logarithmic function is x is greater than 0. There's no way for this to be negative. It's not in the domain, because when you take e, the base, and raise it to a power, no matter what power it is, there's no way to get a negative. So this actually has no solution. However, we do now see that that is where we find the natural log button in case we needed to do a different problem like natural log of 5 or something like that. And then the next one, log base 2 of 31. Okay, so depending on your calculator, you may or may not have a way to do log base, log base 2 of 31. So I'll show you on my calculator. I go into math, and then I go down quite a ways. You can also get there going up. It loops around. I have a function called log base. So once I press that, I can put the base in there, whatever base I want, and I can put the 31 in there. Now, this feature of a calculator is relatively new, just in the last few years. So if your calculator doesn't do it, there is a workaround for this. Used to be calculators didn't do any logarithms and people just looked up logarithms in a table in the back of the book. So we would round this to 4.954. Now, there is a shortcut to find the log base on your calculator. You can press alpha and then window. That takes you to the F2 menu, which is a shortcut menu, and there you see number 5 is log base. So if you remember that shortcut, it's just a little bit faster way to get there. If you don't have log base at all, here's what you can do. You can do log base 10 of 31, close the parentheses, divided by log base 10 of 2. This is called the change of base formula, which we'll talk about more later. Notice you get the same thing. Or you can do natural log of 31, close parentheses, divided by natural log of 2. It doesn't matter what base you use, as long as you put the numbers in the proper places, you'll get the same answer. Okay, so here's your assignment. And it looks like a lot of problems, but these are very short problems. There's no work to show. They're going to go very quickly. And this is something new, so I really think you need the practice to get the idea down and to kind of get the method flowing for yourself. So I do want to give you all these problems, and you're going to be just fine. Thanks, everybody.